Okay, so should we get started? All right, why don't you put on your slide, Rachel? And we'll go from there. Okay, yep, that looks good. I hope everybody can see it also. I think they can. So welcome everybody to the fall season of the Imagine OneWorld seminar. So we're going to be having weekly talks starting now, so you can check our webpage for the lineup of speakers. So the first speaker to get us started is Rachel Ward from University of Texas at Austin. Rachel has done quite a bit of work in many areas, including machine learning, data science, harmonic analysis, even theoretical computer science. So today she's going to give a talk about weighted optimization, better generalization via smoother interpolation. Go ahead, Rachel.
Thank you, Fidel. Thank you for the invitation. Good morning, good afternoon, good evening, everyone. So I want to talk about sort of weighted optimization. This is inspired by sort of a very intriguing open question phenomenon that has been observed in large-scale neural network optimization, which is that these optimization problems, these nonlinear regression problems, seem to have best performance in the over-parameterized regime, meaning the number of parameters in the model is taken to be far greater than the size of the training data. And that sort of goes against classic wisdom in machine learning and statistics, which says the number of parameters should be smaller than the size of the training data to avoid overfitting. So we're going to talk about a sort of a new perspective on this phenomenon using sort of wisdom from Fourier analysis and compressive sensing to sort of demystify this a little bit by giving some rigorous understanding of this phenomenon of sort of double descent behavior of the performance in a linear interpolation setting, and then connect this to sort of how to parameterize neural network optimization guided by this theory. So that's what we're talking about today. And I want to mention that this project was led by my student, Gail Xi, and I am just sort of the communicator of this. She helped write a lot of these slides, and I haven't looked at every single slide yet that I'm going to talk about, so this should be fun. But in any case, let's start with some background. In this talk, we're going to be talking about regression or interpolation. Neural network optimization is often just a really, really giant regression problem in the interpolation regime. Where we just fit a function to a set of training data exactly, take the, and observe how well it generalizes. So regression in the general setup is we have n training data, xj, coming from a domain, a one-dimensional or 100-dimensional or 1,000-dimensional domain. The data is corresponding to an unknown function, noiseless or noisy, a little bit noisy. We fit the data with a hypothesis class of size p by solving for a set of p parameters that minimize the empirical risk function below, just the sum of squares. The classical wisdom in statistics, machine learning, is presented in that p, the number of parameters in the hypothesis class, the model, should be chosen very carefully. If p is chosen to be too small, as in this underfitting picture, say p is just hypothesis class is linear functions, then you're not going to fit the data very well. So you're not going to have good performance. If p is taken to be too large, as in this overfitting picture, then you fit the data too well. So you fit all of the training data exactly, but then it doesn't generalize well in the sense when you see data, new data coming in, it's not going to get that data well. So there's some sweet spot, appropriate capacity, as in this sort of risk bias curve here, which is pretty classical. There's a sweet spot which you could find by, say, cross-validation, where the training error is pretty small, and the generalization error, or how well the function fits new data points in the future, is about as good as it can be. Now, this is a sort of a classical concept, but this goes completely against what happens in modern large-scale neural network optimization. Modern neural networks are, as I said, nonlinear regression functions with very nonlinear hypothesis classes, f sub theta. But still, they're trained to minimize often an empirical risk, where a set of parameters theta that minimizes this risk is found by gradient descent, really simple optimization methods like stochastic gradient descent. And they found empirically over the years that by taking p, the number of parameters in these nonlinear models, to be much bigger than n, the empirical L2 risk is trained to 0 for one. So it's interpolated. The training data is fit exactly. And also the generalization error does not get larger. The generalization error gets smaller as p gets bigger and bigger. So neural networks, modern neural networks, are often implemented in the over-parameterized regime. So what the heck is going on? So the first thing I mentioned, which is that in this over-parameterized regime, we see that gradient descent or even stochastic gradient descent can find global minimizers of these highly non-convex optimization problems. So global minimizers where the empirical risk function is 0. That's still not understood because non-convex optimization is classically very hard to prove anything about finding global minimizers. But we'll just take this as something that's true, and we'll talk about this another day. What we want to talk is that the over-parameterized setting, where the training error is 0, does not lead to overfitting in general. As the model complexity increases, the test error continues to decrease in the over-parameterized regime. See, for example, this is a particular neural net architecture, ResNet 18. We see that as we increase the width on a particular data set, cipher 10, with some noise, as the number of parameters here in this x-axis increases and we go beyond the classical bias variance trade-off, this line is sort of where I had cut off on the previous slide. We go beyond this line into the interpolation threshold where we're fitting the data exactly. The training error down here is 0 because we're interpolating, and the generalization error, the performance on data that was held out, and then we test it with, continues to decrease. And so this has been dubbed the double descent phenomenon from neural networks. This is the phenomenon that if we have this original bias variance trade-off domain in the under-parameterized regime, if we can extend the domain, then the risk descends a second time, often to a performance error that's even smaller than the first descent. Now, what's been being understood in the last few years, and what we're going to talk about here, is that this isn't actually some phenomenon of amazing mystery belonging to complicated neural networks, but it's rather something universal, this double descent phenomenon. It can, we can see the same phenomenon in very simple linear regression or interpolation problems. So we're going to demystify this phenomenon a bit, but it doesn't always happen. When do we have double descent? When can we benefit from just having a hypothesis class and just over parameterizing it and not having to worry about cross-validation or early stopping or overfitting. Definitely doesn't always happen. So what are the favorable conditions? Okay. So now let's talk about linear regression or interpolation. This is a subset of the previous slide on regression or interpolation more generally. So linear regression or interpolation with P features is when we fit our training data to a hypothesis class that's linear. We fix a basis a priori, a feature basis, we'll say. So these are functions phi1, phi2, phi p. These are our features that we fix a priori, and we just do the regression problem where the parameters are represent the best linear combination of these features that fits the training data. So in the linear regression problem, we just are minimizing to find an optimal set of parameters representing the best linear combination of a set of P features. And so we can write this as a matrix problem. The features that are fixed give us a feature matrix phi. The training data gives us where these features are evaluated. So we have the features representing the columns and the training data points representing the rows, and we get a feature matrix phi. And we just want to solve for an optimal coefficient vector theta that minimizes phi theta minus y Euclidean norm squared. Okay, in the under-parameterized regime, the classic regime, phi is going to be a tall, thin matrix, and there will be a unique least squares parameter vector theta, which gives us the smallest value of this least squares error. In the over-parameterized or modern regime, phi will be a short, fat matrix having a null space, so there are infinitely many possible parameter vectors theta which fit the data exactly, which give phi theta equals to y. So 0 empirical risk. And so how well an optimization algorithm does in generalization depends on the implicit bias of that particular algorithm towards one vector theta out of these possibly infinitely many. So just here as an example with, say, Fourier series features, the phi j are the complex exponential basis and up to whatever truncation of the first P Fourier series features you want. And this corresponds to just Fourier series interpolation or regression of functions. Motivated by neural networks are optimized with the simplest possible optimization because the data sizes are so large, there's nothing more complicated that's computationally possible. So that optimization algorithm for coming from neural network regression is just gradient descent. And as it turns out, in the linear regression or linear interpolation setting where the features are fixed, okay, we know the implicit bias of gradient descent. It's a well-established thing. The implicit bias of gradient descent for linear regression or interpolation is just towards the solution, the parameter vector solution theta of minimal L2 norm, which fits the data exactly. So we have an exact expression for this minimal L2 norm solution in terms of the pseudo inverse of the feature matrix phi. And so now, if we want to understand this double descent or behavior in the over-parameterized regime for linear regression problems, we've reduced this to a very classical sort of problem in inverse problems, which is let's try to understand the risk of minimal L2 norm solutions to overdetermined linear systems. Given you need some sort of random model somewhere if we're going to get some sort of expressions. But let's try to do this and understand when we get a benefit of overparameterization and when we don't. I know that there are not any questions, but if someone has a question or a clarification, just put it in the Q&A and I'll try to address it. Okay, so I hope that the problem is clear. Now we're going to ask, when can we see low generalization error in the overparameterized regime, or in the setting where this feature matrix phi is very fat as it gets sort of fatter and fatter and fatter, without in just the linear interpolation setting. So going back to just this Fourier series model, because fitting data coming from a function with a truncated Fourier series is just so classical. That's why I'm focusing on that here. I just want to start by saying that at first glance, it still might seem counterintuitive that we could not see overfitting as we increase the size of the model. Here's just a function f of x equals 2.5 times x cubed minus x. That's the function in green here. We have some noisy observations of this function. So xy pairs, where y is equal to f of x plus a little bit of noise. Okay, that's here. And now the orange function on these plots is us fitting by solving for the minimal L2 norm, solving by fitting to a truncated Fourier series in the underdetermined and then the over-parameterized setting here. So in the underparameterized setting, this is just the sort of classical best approximation with just nothing there, just a line. And then here, Fourier series only up to the quadratic. So 0, 1, 2. So only 3 degrees of freedom here. This is just the unique least squares solution. This is in the case where p equals n. So here we're fitting with Fourier series up to degree 15 when we have 15 data points. So we see a little bit of overfitting there. And here we solve for the function whose first 75, which is a Fourier series of degree 75, where the Fourier series coefficients have minimal L2 norm. So among all of the possible Fourier series which interpolate the data exactly, this one has Fourier series coefficients minimal L2 norm. This is terribly overfitting. You do not want to interpolate data with this function with a function that looks like this. What's happening? The minimal L2 norm parametric solution, it's just dying to, once it fits a data point, go back down to the origin. See, that's what's happening here. So it's huge oscillation. So it goes up, fits a data point, and then it just has to get back down to the origin, then fits another data point, then gets this huge oscillation because it's the minimal L2 norm Fourier series coefficient solution. And we know that by Parseval's identity, the L2 norm of the Fourier series coefficients of a function is equal to the functional L2 norm. The L2 norm, the integral of the function squared over the domain. So it's the optimization problem is solving for a function of minimal area under the curve. So that's why it's getting back down to the origin over and over and over again and oscillating and overfitting. Okay, so this might make it seem like a minimal L2 norm coefficient solution is a terrible thing to try to have an implicit bias towards in the overparameterized regime. Sorry. So how is this working in neural networks where there's a bias towards this sort of thing? So now we try to get some wisdom from compressive sensing. Compressive sensing about a decade ago was all about having good regularizers or good biases, explicit bias towards coefficient solutions in the over-determined regime, short fat matrix, that are good in the sense that they don't overfit because they're sparsity promoting. So compressed sensing was all about minimal L1 norm coefficient solutions. Okay, so this is in green, compressive sensing. So this is from about a decade ago, a paper I wrote with Holger Rauhut, where we're looking at interpolation of smooth functions which are both smooth and sparse in the sense of it's a high dimensional function and we expect it only to have a few important directions where it's changing among the high dimensions. So most of the directions it won't be changing. So smooth and sparse in that sense, but this is just a one-dimensional figure. This is a classic smooth function. Maybe we see some data. And we were saying that a good idea is to interpolate the data points with not a L1 coefficient L1 norm. So for example, again, think of the features as being, say, Fourier series features, but they could be any orthonormal feature basis. Actually, the coefficient vector of minimal L1 norm solution is not good. We see overfitting. There's just this, what you see is a bunch of runs of an experiment where we generate the training data points from some probability distribution. So we generate a new set of these training data points and we plot the minimal L1 norm coefficient solution. This shows there's a lot of overfitting. But if we solve for a solution of minimal weighted L1 norm, where there's a bias towards lower frequency features so that we are dampening down the high frequency features, which is leading to overfitting, we see less overfitting. And depending on if we get the weights, choose the weights correctly, when we ask for a weighted L1 norm interpolating solution, we see remarkably good agreement between the underlying function, which is unknown, and the function, which is the minimal weighted L1 norm Fourier series coefficient solution. So now we're saying this modern problem, which is modern because it's motivated by neural networks, is actually even more classical and even more simple than L1 norm. It's just the L2 norm. So gradient descent, we're saying, will converge to a minimal L2 norm solution instead of L1. Okay. And we had done experiments with weighted L2 norm just to compare to weighted L1 norm, and we were surprised a decade ago, or 8 years ago, sorry, that weighted L2 norm solutions also did pretty good, almost as well as weighted L1 norm solutions. And that's a much simpler thing to find, a weighted L2 norm in Fourier series interpolating function. It has a closed form expression, the parameters. And the intuition is very clear why weighted L2 norm Fourier series solutions should be less overfitting. You choose the weights to grow with the derivative of the corresponding complex exponential feature, so that you're down weighting the high frequency features and you're up weighting the low frequency features. The underlying assumption is that the function that you're fitting is smooth, because we know that smooth functions are characterized by the decay in their Fourier series coefficients. So if your underlying function is smooth, its real Fourier series coefficients have decay, and then you fit that with an algorithm which has a bias towards a minimal L2 norm Fourier series coefficient solution with the same general decay in the weights, you're going to get a really good fit. And so then going back to the neural network, we're saying, can we get some rigorous bounds on understanding how weighting really is everything for whether or not you get overfitting or not. And let me just say that finding a weighted L2 norm solution is exactly the same as just normalizing the columns of your feature matrix phi. So here, if you have, say, Fourier series features, normalizing the jth feature by a weight omega j, here we see something good if omega j is proportional to the derivative of, is the same as a weighted L2 by change of variables. So normalizing the feature matrix or looking for a weighted L2 norm solution is the same there. Okay, so we're going to try to explain in particular a figure that was in this Belkin et al. 2019 paper, 2 models of double descent for weak features. This paper and another paper have been very influential in coining the term double descent phenomenon in deep learning, and really pointing out that this over-parameterization is not some phenomenon of deep learning, it's a more universal phenomenon that's also observed in just linear problems. So here they plotted in this paper these experiments that they didn't have theory for, which showed here this middle, we see the risk really goes down as the number of features P gets very large, and showing also that the weighting of the features, the normalizing of the features, according to a model of underlying smoothness of the function, really leads to low generalization in the over-parameterized regime, where not doing this normalization or weighting, you see that you don't get the benefit of over-parameterization. Okay, so they had some sort of initial theory in an isotropic setting, which actually doesn't explain the benefit of choosing the feature weights to incorporate smoothness. And they had some asymptotic theory, but so they could explain this first plot, but not this sort of interesting double descent phenomenon. So we were motivated to try to understand this rigorously. Okay, so now I want to give you the setting under which we can derive some sort of sharp bounds on the risk. I think there's a Q&A here, but I can't actually read it, I guess, because my screen's open. I'm actually Zoom challenged. Still, it's very sad.
So the question is from David Hogg. Is the weighted L2 Fourier series identical to the Gaussian process mean with a particular kernel as P goes to infinity, or a Wiener filter?
Ooh, cool. That would be cool. Maybe, I don't know. I like that. Thank you. So the model that we're going to analyze is a random model of smooth functions. So we're going to assume that we're seeing training data from some underlying function, and it's not an arbitrary underlying function, but it's sort of a random smooth function. So we have to have this randomness. So how do you generate a random smooth function? What does that even mean? So a well-defined sort of way of generating a random smooth function is to say, I'm going to have a function with a finite Fourier series expansion. So just like in the range of the lowest 1,000 complex exponentials. So it's coming from a finite dimensional function class. And I'm going to generate, its Fourier series are going to be random variables. Its Fourier series coefficients are random variables with a decay. So non-isotropic random vector. So the ith Fourier series coefficient, I equals 0, 1, 2, 3, 4, is basically going, they're all going to be zero mean, and the ith one is going to have variance proportional to 1 over I squared. Okay, so this is sort of like a quadratically decaying Fourier series. So that's a model for a function which is differentiable and has a certain Sobolev norm. And of course, we can make this I to the -2. We can make this -2 a parameter Q. So Q is going to, from now on, be the rate of decay or the degree of non-isotropicity in the model for the underlying smooth function. Okay. Okay, and if we're going to consider Fourier series features here to begin with, then minimizing or penalizing a weighted L2 coefficient norm is equivalent to a smoothness norm. So this is where we can use wisdom from Fourier analysis. We know that due to the duality between frequency and time domain, that looking for a minimal weighted Fourier series L2 coefficient solution, that is equivalent to asking to interpolate with a the function in the span of the first so many Fourier series of minimal Sobolev norm, where the Sobolev norm is just the L2 norm of the function squared plus the L2 norm of the rth derivative of the function squared, where R is Q here. I'm really sorry, but Q is supposed to be R. Okay. Actually, no. See, this is what I said about not looking at all the slides exactly. Okay, so there are two parameters here. There's the actual underlying smooth function, and it's going to be generated using this non-isotropic Fourier series model with parameter R. So it's going to have a certain rate of decay, and then we're going to look at risk bounds for the interpolating function of minimal weighted L2 norm with weights proportional to the Qth derivative. So Q isn't necessarily equal to R, but it's going to be best when Q equals R. That's when our model matches our underlying class exactly. Okay. Anyway, so okay, so we're going to give expressions for the risk when considering this weighted optimization using this reparameterization. Okay. Okay, but this is just normalizing the Fourier series features, dividing the complex exponential basis functions by the jth one by j, by j to the something, and we're going to see how that influences everything. Okay, so here is our model. The randomness is in this random Fourier series model with R decaying coefficients. So we assume that we're getting training data associated to a random function in this class. We're going to observe the training samples at equispaced points on the domain. In this case, the domain is the interval -1 to 1, because we're just talking about Fourier series, so we're in 1D. So that's our points are at equispaced points on the domain. And then the sample discrete Fourier matrix is our feature matrix. So this is just a short, fat matrix, a subsampled discrete Fourier matrix. And we are going to, among all the infinitely many possible interpolating functions in the overparameterized regime, we are going to analyze the performance of the particular interpolating function whose Fourier series expansion, its coefficients have minimal LQ. weighted L2 norm with weights proportional to this growing like this Q. And we're also going to get an expression in the under-parameterized setting, the least squares setting, where the weights don't matter. There's just a unique least squares Fourier series solution. But we're going to get a bound anyway, in that case, to compare. And I've been saying performance, and I've been saying risk, and I've been throwing it around, but I want to just write it out here. The risk, in the case where our features are Fourier series features, which are orthonormal features, Parseval's identity tells us that we can calculate the risk, or just the functional L2 norm error between our underlying function and the weighted L2 norm interpolating function is exactly the same as just the coefficient L2 norm between the unknown Fourier series coefficients and the ones, the theta hat, which are the ones we're looking at. Okay, so this is what we want to express them for. And it's really hard to get a bound on this risk. Okay, the expectation is because our class is random. It's really hard to get a bound on this because this theta hat is a random variable depending on theta. Okay, and it's a random vector gotten from a pseudo inverse solution, which is a matrix, which itself is random. So it's a nonlinear function of a random variable. So we're only going to be able to get nice expressions on the next page for this, as far as we can see, because of the assumption that our training data are equispaced, that our training sample points are equispaced points. Otherwise, I don't know how to get something nice if we just replace that or ease up that assumption to be uniformly IID training data. I don't know. We have to use very nice properties of the partial Fourier matrix. But we can, and using a bunch of kind of technical analysis, we can say, we can give sort of these risk bounds in terms of R, which is the decay of the Fourier series coefficients in the underlying random function. And in terms of Q, the weights that we apply in the optimization algorithm to Q is like our guess of what the smoothness is, what the decay is. So remember, Q equals R is sort of the best. But we get this risk bound. We said, okay, as the number of parameters in our Fourier series model increases, the risk is going to decrease in the sense that this second term is going to go to 0. So we are going to get a decrease in the risk with overparameterization as long as the underlying random function is smooth with smoothness parameter greater than a half. Okay, and we're going to say that in certain situations, our exact risk expression is a double descent. It is a curve which in the underparameterized regime has a first local minimum, and then it goes up when P approaches N from the underparameterized regime, and then it descends again to a lower risk in the overparameterized regime.
Rachel, there's a question from Soledad. The question is the expectation condition on the training data?
No, the only randomness comes from the training data. That is the expectation, is expectation over the Fourier series coefficients, which is a random vector in the model from which we observe through the training data. So there's no conditional expectation. That's the one and only source of randomness in the This is expectation with respect to the theta is the true underlying Fourier series coefficients. Does that make sense? Okay, so let me know if that's not clear. This is a bit inverted. The usual setting in the statistics, sort of in the more traditional or the more statistical way of analyzing this, is that the underlying function is fixed. The underlying function is not necessarily random, but the training data are randomly sampled on the domain. The training, so there's randomness there and that's closer to the setting we would like to be able to analyze, because in neural networks and high dimensional setting, it's more natural that you're assuming your training data is random. But here we don't know how to do that. So our training data is fixed at fixed location, but it's observations of a random function. Okay, so I know this is a lot of variables, especially for early in the morning or any time of day.
Can I ask another question?
That sounds great to me.
So when you had this reparametrization, the goal of it was to improve the condition number on this phi transpose phi matrix that you invert when you solve the least squares?
More or less, yes.
Okay. Thank you.
I'm not sure if that's exactly the object whose condition number we're trying to minimize the most, but that more or less, yes. Okay, so here are just some plots of the risk expressions that we get. This is the number of features, and the orange is if we incorporate the correct normalization of the features, given to incorporate the smoothness model. And blue is if we don't do any sort of normalization of the Fourier features, we just do plain Fourier series features and sort of unweighted parametric L2 norm solution. And we see a bigger and bigger discrepancy between what happens in the over-parameterized regime if we do the unweighted minimization versus the weighted, what's the difference in these three pictures is the underlying model of smooth functions is getting smoother and smoother. Okay, so if the underlying function becomes more and more smooth, then taking advantage of that smoothness in normalizing our features for optimization makes all the difference between whether we see a double descent or even just a single descent as we increase the number of parameters compared to not. It's everything. If we normalize the features correctly, has everything to do with if and when we see lower and better performance of the optimization algorithm in the over-parameterized regime. And I'm just saying this 2 or maybe 3 times because I haven't seen this there's been a lot of literature lately on analyzing this double descent phenomenon in linear or non-linear setting, wherever. But I'm saying even in the simple linear setting and a simple set of fixed features, the features are, say, Fourier features, whether or not you can benefit from over-parameterization or not has everything to do with whether you normalize the features correctly in terms of to match or to get close to matching the smoothness prior sort of in the function we're trying to recover, the unknown function from which the training data comes from. Okay. And then we have a bunch more plots showing that Q does not have to equal R exactly. We don't have to know the rate of decay of the Fourier series exactly of the function we are trying to recover. But if we just, the closer we can get in our optimization, the closer we can match, the better. But we don't have to do that exactly. Now, I'm running a little bit short on time. I'm sorry for going too slowly. Just to look at these last two pictures, just to really emphasize again, whether we can get a good interpolating function in the overparameterized regime with a sort of weighted L2 coefficient has everything to do with the weights. Whether we have just an oscillating to death function that's terrible interpolator versus one that's good has everything to do with if we normalize the features correctly with these weights. We need the randomness in our model. Otherwise, I could construct a counter example of a smooth function that we can't get a good risk bound for. So I just wanted to say our model is all the assumptions there are necessary. But it'd be nice if we could get some theory for random samples instead of equispaced samples. And we basically generalized some sort of first results in this paper I mentioned of Belkin et al., which only considered isotropic features. So we sort of generalized that. There are challenges that are technical. And I just want to mention that we analyze theory for a univariate Fourier series model, which might seem to say nothing about what's going on with deep neural networks. But in fact, there is a connection in that if we look more closely at the type of neural network optimization problems that give rise to this double descent phenomenon in practice, they are highly nonlinear. But they also, the ones that we really see this phenomenon with, are reparametrized in a way to implicitly have these weights, which downweight high frequency features and upweight low frequency features. It's there in terms of what's called weight normalization, or more loosely batch normalization, which is a reparameterization that is used in practice, which reparameterizes the optimization problem to not just be a simple L2 empirical risk minimization, but to divide the parameters in the neural network model by their norms, which is equivalent to weighting the Fourier series like we did by normalizing them by their gradients, essentially. So there's something there. There's an implicit reparameterization to bias towards smooth interpolations in neural networks in the form of these batch and weight normalizations. And this is just experiments on neural networks, just verifying that the generalization there is better when one has these reparameterizations. So the big question now is, we have a sort of precise understanding of this behavior in a simple Fourier series interpolation setting, one-dimensional. And then we have a sort of moral, how it has a sort of moral equivalence to the way neural networks are, the optimization problems are reparameterized to encourage lower frequency types of features and to discourage high frequency features, thus promoting smoother interpolations, which would thus make sense as to why we see increasingly good performance with more and more features. But of course, we need to fill this gap rigorously. And also, we know that there's a lot more going on than just smoothness in neural networks. It's not just the smoothest interpolator that's going on. There's also sparsity, invariances to rotations and other things. And there's a lot more going on that needs to be explained as to why the performance of neural networks is better than expected, I would say. This is just some guidance for other technical extensions, so the references, and thank you.
Thanks very much, Rachel. That was a very good and very nice, interesting talk. If the audience have any questions at all, maybe they could just raise their hand or put something on the chat, and I will allow you to talk. Okay, David, I'm going to let you talk. David Hogg. Allowed to talk. Here we go. David?
Cool. Can you hear me?
Yeah.
So I love this. Soledad also asked the question. Soledad and I have been working on some things on the other side of this with these more random models, but I really like this structured Fourier model because you can control the smoothness of the model you're thinking about. And the question I had was this normalization. It makes a lot of sense to me that you get very good risk properties or whatever performance on test data if you use the correct normalization of the features. And I was wondering if that relates somehow to Bayesian inference, because using the correct normalization of the features is sort of like using correct prior information or putting some kind of, if you think of it as a probabilistic model, like the maximum of a probabilistic model, it looks like you're putting correct prior information. So I'm wondering if there's a relationship between this and Bayesian inference.
It really seems like it, right?
Yeah, for sure.
So my answer to that is it must be. There must be a Bayesian perspective on this. But there are also some crucial properties that we used in this particular setup that I wouldn't know how to extend. Again, this equispaced samples, which gives rise to a partial Fourier matrix with a circulant structure that we can get used to cancel out certain things in this, because this risk is a very nonlinear sort of expression we're trying to control. There's a pseudo inverse of this feature matrix, and only using the circulant structure when the samples are equispaced training data allows us to commute certain parts of this matrix to cancel things out and get this nice expression for how the risk decreases with N and P. It would be wonderful if one could give a more general.
Yeah, we also are facing that issue where it looks like it's hard to get expressions in the non-asymptotic regime unless you have some structure. Because if you have an unstructured, like random set of points, those phi matrices or phi transpose or whatever can have really crazy eigenvalues.
Yeah, probably we're just trying to do too much, and we should just relax and say, let's just, asymptotic is fine.
Right. Yeah.
As long as it's asymptotic, as N and P go together asymptotically.
I bet I would put money that the asymptotic result you have now would be correct for randomly chosen locations in the limit. Like, I bet they converge.
Yes, I would say that that's correct, as long as P is like greater than N log N. When P is close to N, they're very different. When P is equal to N in the random samples, you get an explosion, you get a pole.
Good, that makes sense, yeah.
And the equispaced samples, you don't get a pole, you just get a little hump.
Yeah, that sounds right.
Other questions? I don't see anything in the Q&A. I don't see anything in the chat.
It's okay. People can email me or.
Is the work already up on archive?
Yes, same name.
Same name. Okay, very good. This is very interesting. Maybe I could just ask a quick question. You mentioned something about, if you go to a real deep network where you have all kinds of other things going on, like symmetries and so on. Mm-hmm. How is that restricting or being captured by the kind of analysis that you're doing here?
I would say that the type of analysis we're doing here is orthogonal to that. it's sort of just isolating the smoothness aspect. Sort of like, it's sort of just like sort of a sanity check that at least at a bare minimum, your neural network optimization in the over-parameterized regime should have an implicit bias towards a smooth interpolator. Rather than this wiggly one that oscillates to death by going back. So, but then on top of that, it should be not just smooth, but also there's more going on, higher order model assumptions that are being implicitly incorporated that we don't understand yet.
Very interesting. Well, if there are no more questions, our time is actually up. It's almost 11 here in East Coast. Well, we want to thank you again, Rachel, for starting our seminar series in the fall and with a wonderful talk. So we'll see you again, everybody, next week. Thanks very much. Take care.
Bye. Thank you.